Okay, so I'm happy to introduce our next speaker, who is Cyril Labbe, and he will tell us about the one-dimensional Anderson model with white noise potential. Please.
Okay, thanks a lot. Thanks a lot for the invitation. It's a real pleasure to be here. It's a very nice conference. So it's a joint talk with Laure Dumas, and it's about a continuous operator in 1D. So let me introduce the operator. So it acts on function from R to R. So you have minus Laplacian plus f times psi, okay, so on R. And psi here is a white noise. In dimension 1. So there are different ways of defining white noise. Let me define it in that way. So you take a Brownian motion B on R. So two-sided Brownian motion. And psi can be defined as a derivative in the sense of distribution of B. Okay? So B is not differentiable, but it can be differentiated in the sense of distribution. And so you get a random distribution, which has very nice properties. Okay, so you have a stationarity property of psi. Okay, so if you evaluate psi against a function, you can shape this function, and in law you get the same thing. And you have an independence property, that is, if you test psi on disjoint set, you get independent random variables. Okay. Right. But it's distribution valued, so there are some issues related to this irregularity that I will comment later on. Okay.
And it's Gaussian.
And it's Gaussian. And I think I should have turned it on, and I didn't. Yeah, and I need to introduce the finite volume approximation of the operator. So you take exactly the same one, except that you restrict to a bounded box of length L. Okay. Fine. So the plan of this first talk is first to present a result of Anderson localization for H. So I won't spend too much time on this part. Then I will discuss issues coming from the singularity of psi. Okay, so in the first part I will assume that H is well defined, and then I will come back to this point in the second part. In particular, issues about the domain of H. And I will also try to make comments about what happens in higher dimension. And finally, I will talk about the behavior of the finite volume operator of the spectrum of HL in the limit L goes to infinity. Okay, so I need to cover. This is the core of the talk, and I need to cover it because Laure afterwards this afternoon will continue on some specific part of this description of the spectrum. Okay. Fine. So let me start with the Anderson localization result. Fine. So it's a recent result with Laure. So what did we get? So we showed that almost surely H can be constructed as a self-adjoint operator on a dense subset of L2 of R. It's with the spectrum which equals R. But it's pure points. And with exponentially localized eigenfunctions. Okay, so more precisely, what does it mean? It means if you take a pair lambda, phi eigenvalue, eigenfunction, then the following quantities, so the log of the square root of phi t squared plus the derivative of phi squared, this quantity, it converges almost surely when t goes to plus or minus infinity to some constant, gamma lambda. And this gamma lambda is the Lyapunov exponent associated to this problem. So it's a deterministic quantity. It's exactly the same quantity that appears in Sasha Selin's talk on Sunday. And it's completely explicit. Okay, so you can give integral formulas for this Lyapunov exponent. Okay, so maybe just to draw a picture to give some ideas of what is going on. So you have, so what should a typical eigenfunction look like? You should have some point where it is essentially maximal. So, and this point is, of course, random, so say u lambda. And then, okay, so my picture won't, I should write it somewhere else. So, sorry? Okay, thanks for, it's fine for everyone if I, no, it's not fine. Okay, so yeah, so let me draw the picture here. So if you look at this, at such an eigenfunction, what you should see is some point u lambda which is random, where the function is maximal, and from this point you would see typically oscillations like this, which are random, and basically the absolute value of phi decays exponentially from u. Okay, so the shape that you see here is something like e to the gamma lambda t minus u. Okay, just to give an idea of what the eigenfunction look like. Okay, so it's a typical result of Anderson localization. Let me make a little comment. So we have about the spectrum, we have a dense countable collection of eigenvalues, of genuine eigenvalues, yeah. So, and that's the fact that it is dense explains why the whole spectrum, the spectrum is the whole line R. Okay. Fine. So maybe a few remarks about this result. So it's totally expected, of course, because we are in one dimension. Okay, so it's in one dimension, so it's expected to have such a Anderson localization. But the little issue here is the fact that psi is a white noise, is irregular. Yeah, and maybe a second comment is about the proof. So I don't want to spend too much time on this theorem, but I would just want to say that we have actually two proofs for this result. And the first one follow the works by Molchanov and later Ron Carmona. I think it's 81. And the second one is different, and it follows the approach of Kotani from 84, I think, and then Kotani and Simon. So maybe very briefly, in this first approach, you start from estimates on the eigenfunction on a bounded box, so on the eigenfunction of HL, and then you use the convergence of the spectral measure to propagate the estimate to the full line. And in the second case, it's different. It's using the Furstenberg-Osseledek result that were presented on Sunday, that allows you to say that for a given lambda, almost surely you have an exponential splitting of the eigenproblem. But then you have this issue that it's true for a given lambda almost surely, but it's not true simultaneously for all lambdas. So permuting these two things is difficult. And then there is a trick by Kotani, by some averaging property, averaging scheme that allows you to do that. Fine. So now I'd like to say a few words about the singularity of white noise. So singularity of the fact that white noise is irregular has some consequences, and one of them is about the domain. So the domain of H or HL is not obvious, and I'll try to give some idea of why this domain is not easy to guess or to determine. Okay, so the usual approach to construct such an operator is to start from smooth function, so C-infinity function with compact support, on which the operator should act nicely, and then to increase the set of functions and close the operator, and given the boundary conditions, prove that you have self-adjoint extensions. So let's try to apply this scheme. So you start from some function f, which is C-infinity with compact support on R, and you apply the operator. So what do you get? So HF, you get the second derivative of f. So since f is infinity, this function is very nice. You still have something which is in L2, plus f times psi. And the point here is that psi is irregular everywhere. Okay, so think of the derivative of a Brownian motion. So everywhere you have something which is oscillating very fast. And then the consequence is that if you multiply a function, even if it's smooth, with such a distribution, you always get a distribution. Okay, except if f is 0, but as soon as f is non-zero, you are sure that this quantity is not in L2, and therefore the sum of these two objects cannot be in L2. Okay, and it's true simultaneously for all f. So what does it mean? It means that if f is C-infinity with compact support, f cannot be in the domain, if the domain exists. Okay, so it's bad news. But actually, it also gives some idea of what f should look like if you want f to be in the domain. So it says that if you continue in this sort of idea, you see that if f is in the domain, if the domain exists, then indeed you need the second derivative of f not to be a function. You need the second derivative to be a distribution, so that the two terms separately would be distributions, but they should compensate each other in a subtle way, in such a way that the sum is in L2. Okay? So what does it mean? It means you need the derivative of f, the second derivative of f, to look like psi at small scale. Okay. So you need f to be not too regular, and the domain a priori should be made of functions which are random and not too regular. Okay. Fine.
So even though the operator is not bounded from below, you find the well-defined quadratic form on that doesn't work.
Okay, so that's my next comment. So here we see that the domain seems a bit subtle, and so one way to circumvent this issue would be to go through via quadratic forms. And indeed, there is a construction of HL, so in finite volume, via the Dirichlet form, so quadratic forms, and it's due to Fukushima and Nakao. In 77. Okay, so it happens that if you look at the Dirichlet form, the regularity of the potential is less problematic. And it happens that in 1D, the quadratic form is very nice. It has a domain which is deterministic, which is H1, and you can build the Dirichlet form, and then you can prove that there is some associated self-adjoint operator HM. But the thing is, this doesn't apply on the full space. Because the spectrum is not bounded from below, so you don't have a bounded from below Dirichlet form, so it's not possible to apply this type of technique to construct the operator.
There's work on quadratic forms that now.
Okay, I would be interested in discussing that, but okay. And then, okay, so on the full line, there is another way of building the operator. So you can construct H and HM with something different, which is the theory of generalized Sturm-Liouville operator. So let me give a little idea of what is at stake here. So the theory of Sturm-Liouville operators would apply to operators like minus f double prime plus f times v, with a v which is a function which is therefore not a distribution like the white noise. And the idea is to try to adapt, to generalize this theory to a setting where v can be allowed to be distribution valued. And mainly the point here is to allow for functions which are not twice differentiable. Okay, so we saw in this heuristic argument that f cannot be twice differentiable if you want it to be in the domain. Yes?
I have a basic question. You said that this operator is on the subset of M2, but you demand that f is a distribution.
No, f double prime is a distribution. So if you integrate twice, okay, so f, its second derivative should look like a distribution, but when you integrate it twice, you have basically something that looks like the integral of a Brownian motion. So it's a function which is held down 3 half. Okay. Right, so I was saying we need to allow for functions which are not twice differentiable. And this is what the theory of this generalized theory of a Sturm-Liouville operator allows for. And it's, so very quickly, it's based on this following integration by parts. So you can rewrite this expression in the following way. So you can rewrite it as f prime minus bf prime minus f prime b. Okay, so it's just a computation of distribution. So this equality is true for distribution. But what this writing suggests, it suggests that actually, instead of asking to f to be twice differentiable, which is not the case in the domain, what you could do is to ask to f to be differentiable once, and then to ask to the derivative of f to be such that if you subtract this irregular term, which is not differentiable because b is not differentiable, you could expect that this difference is then differentiable as a function. Okay? And actually this works. You can apply this kind of argument to build the operator, and it's consistent with what I said here. Okay? If you want to impose to the second derivative of f to look like psi, it's equivalent basically to asking f prime to look like b. Okay? So there is a consistency here. Fine. Right, so I'd like now to take this the opportunity to say a few words about what happens in higher dimension. So in higher dimension,
Cyril,
yeah.
can you say somewhat precisely what is that too
Well, the domain, so basically the domain, H or HL, will be the set of function f in L2, which are such that, so f is absolutely continuous, and f prime minus bf is also absolutely continuous, basically. And then you can prove it's a very simple proof, plus boundary conditions, integrability and stuff. So boundary condition if you are in finite domain, integrability. And then, yeah, and you can prove that you have a dense set of such functions. You know, it's very. Sorry. Okay, so either you start with functions which are compactly supported, intersected with this set, and you get the minimal domain, or you take all the functions. Okay, I'm too vague here because it would be a bit long, but either you have these functions which fulfill these conditions and are compactly supported, you take the closure, and you get the minimal domain in finite or infinite volume. And then you can also start from the maximal one, which is basically all functions that would satisfy these conditions. And then in finite volume, they don't match, so you need to add boundary conditions. And in infinite volume, they match because the operator is limit points. Okay, so I don't want to say more about this aspect. So what I want to do is to say a few words about what happens in higher dimension. Because there is a nice connection with another part of probability, which are stochastic PDEs. Okay, so higher dimension, what happens? So you could ask if you can construct minus Laplacian of f plus f times psi on Rd with psi a white noise on Rd. Okay, so by the way, it's the very same operator, very close to the operator that Jan Fyodorov showed in his talk on the first slide. There was a magnetic field, but it's essentially the same. Okay, so of course, these type of issues are even worse in higher dimension. Okay, so white noise is irregular everywhere, so the domain cannot be made of nice functions. And so let me go a little bit further in this direction. Okay, so let me continue this argument. So here, the heuristic would be if f is in the domain, then the Laplacian of f looks like psi. And this means that f should look like the inverse of the Laplacian applied to psi. Fair enough. But then, if f looks like such a random object, when you apply h to such a f, you're going to get product of the form psi times the inverse of the Laplacian applied to psi. Okay, so when you compute the action of h on such a function, naturally you are led to computing quantities like this. Okay? And it happens that this quantity is finite in dimension 1 and is infinite in higher dimension. Okay, so there is a blow-up in the operator in dimension 2 and higher. Okay, and this type of blow-up is exactly of the same, so it's very similar as what appears in stochastic PDEs, in singular stochastic PDEs like KPZ or 543, etc. The very same issues arise. Okay, so you have blow-up due to the singularity of the noise. The noise forces you to have a low regularity for your solutions, but then the nonlinearity of the products are ill-defined. And then it's possible, so you need to renormalize the equation. So you need to subtract some infinite constant, and this can be done using regularity structures, for instance, or para-control distributions. Okay, so it has been done by different people. I will not give any detail on that. But the final form of the operator that you get then is slightly different from the one we started from. So in the end, what you get is something which is formally, which would write like this. Okay, so you need to shift the operator by plus infinity to make sense of it somehow. Okay. And the correct statement, the more precise statement would be if you smooth out the noise at some scale epsilon, you identify a constant that depends on epsilon, which diverges, but which is such that if you add this constant, the sequence of operator converge in some sense. Okay? Then, okay, so it's possible, it's okay in dimension 2 and 3, but it's not possible in higher dimension. So in higher dimension, the equation is supercritical in the sense of Martin Heyer, and you can't apply this kind of theories. The reason being that, okay, so what does supercritical, subcritical mean? It means if you look at this operator at small scale, you ask which term is dominant. So at small scale, is it the Laplacian or is it the noise? And at small scales, what you need to have a negligible nonlinearity product or noise in your, I mean, the ill-defined part should be negligible at small scale. So then the equation is called subcritical. If it's dominant, then it's supercritical. It happened that the scaling of white noise makes the equation supercritical in dimension 4. Like KPZ in dimension 2 is supercritical. Okay. So yeah, there are still some issues about defining properly the operator in the full space. But in the finite domain, these kind of things have been done in detail.
What about Anderson localization at near infinity?
Yeah, it's work in progress. You mean for the full?
Yeah.
It's work in progress. Yeah. It should be true. But yeah. Other questions?
So dimension 2 is related, or it's formally related, or at least dimension formally related to self-intersection of
Yeah. So yeah, true. So actually, so this infinity is actually the limit of some constant C epsilon, okay, which arises when you take a smoothed out noise psi epsilon at scale epsilon. And this C epsilon is like a log in dimension 2. It's log of 1 over epsilon. And in dimension 3, it's 1 over epsilon plus a log. And actually, this constant is the same as what you need to renormalize the self-intersection local time in dimension 2 for the Brownian motion. And in dimension 3, I checked it again this morning because we discussed it with Valiant. This term is what you need to renormalize the expectation of the self-intersection local time in dimension 3. And this is what you need to renormalize the variance. Right. Okay, so that's all for higher dimension. So let me come back to the third goal, which was to understand what happened to the operator in finite volume. Okay, so you may think that once you have understood the behavior on the full space, the operator H, the story is over. But I will try to convince you that there are things to be said if you look at the finite volume version of the operator in the large scale limit, in the large volume limit. Okay. Fine. So let me say a few words about HL for fixed L. So we fix L, and we look at this operator HL. So in that case, HL is bounded from below, so it's a self-adjoint operator on L2 of minus L over 2 L over 2, and it's bounded from below. Okay, so you have the smallest eigenvalue, lambda 1L, then the second smallest, etc. So you have a sequence of eigenvalues, and this sequence goes to plus infinity for fixed L. And I think a good way of thinking of this sequence of eigenvalues is to think of the sequence of eigenvalues of the deterministic operator. So you take the Laplacian on the segment for which you can compute the eigenvalues. They are all positive, explicit. And then you add the noise, and this noise will perturb the eigenvalues. And therefore, these quantities are sort of little perturbation of the eigenvalues of the Dirichlet Laplacian. Okay, and when the size of the segment increases, we want to understand what is the strength of the deformation. Okay, fine. So what did I want to say? Maybe the density of states. So let me introduce the density of states. So it was computed by Halperin in the 60s and Fukushima and Nakao. In 77. So let me recall the definition. So you introduce the counting function for the eigenvalues of the finite volume operator. So you count for a given energy E, the number of eigenvalues of HL that lie below E. You divide by the volume, L, and then you take the limit when L goes to infinity. And it happens that you have an almost sure deterministic limit that you call the integrated density of states. Okay? And then the density of states is simply the derivative with respect to E of this quantity. And it's completely explicit. I mean, it's given by an integral formula, so you can draw a picture. So it looks like this. So you have a Lifshitz tail here, which is like e to the minus, I think it's 8/3 e to the 3/2, something like this. And here it matches, it satisfies a Weil law, so it's something like 2 pi square root of e. Okay, so that's the density of states. Okay, and maybe to compare it with the density of state of the Laplacian, of the deterministic operator minus Laplacian, or minus for the Laplacian, you only have eigenvalues on R plus. Okay, but you have the same behavior for the two operators towards plus infinity. But of course, you don't have eigenvalues for the Laplacian on R minus, and these are produced by the white noise, basically. Okay, the white noise creates eigenvalues on R minus that you don't see with the Laplacian itself.
Is there a simple explicit formula in terms of some kind of integral?
Yeah, there is an explicit, yeah.
Something in terms of area function.
Or an area function?
Yes, in terms of area function.
Yeah, so, okay. Maybe I don't write the
No,
equation.
no, it's useful to know it exists.
And then, okay, so another result I wanted to quote is about the asymptotic behavior of the ground state, so of lambda 1L, as L goes to infinity. So it's a result by McKean from 94. And so what did he show? He showed that if you introduce AL, a deterministic quantity, which is like a log, which behaves like a log, then at first order, lambda 1L behaves like minus AL. And it fluctuates around minus AL like 1 over square root of AL. So, yeah, I think it's something like this. So this whole quantity converges in law when L goes to infinity towards a Gumbel law. Okay, so what does it mean? It means you look at the axis here, and you track the first eigenvalue when L goes to infinity. And what McKean says, he says you should look at a region around AL. So AL goes, minus AL. AL goes to plus infinity logarithmically. So you, at first order, you should track your eigenvalue near minus AL. And in terms of fluctuation, it fluctuates in a tiny window of size 1 over square root of AL. Okay, so maybe lambda 1L would be here. And then lambda 2L would lie nearby, maybe, etc. So our starting point with law, when we started this whole project, we wanted to extend this result not only to the first but to the second case eigenvalue, to understand the joint law of the k first eigenvalues, and also the behavior of the associated eigenfunctions. Okay. And in the end, the goal that we had was the following. So the goal that we had with law then can be phrased in that way. So what are the local statistics of the eigenvalues near some energy E, which may depend on L? Okay, so what do? Basically, you choose some energy E in the spectrum, you zoom around E in such a way that the spacing, the typical spacing between two consecutive eigenvalues is of order 1. Okay, so a priori they are very close to each other, but you zoom inside the spectrum near E and you rescale things in such a way that the spacing is of order 1. And then you ask, what type of statistics do you see? And the associated question was, what is the behavior of the associated eigenfunctions for the same type of energies? Fine. So, so I need to hide the goal. So it appears that we identified 5 regimes of energies that I'm now presenting. And for each regime, we obtained the local statistics of the eigenvalues and also the precise behaviors of the eigenfunctions. Okay, so what are the 5 regimes? So starting from the bottom of the spectrum, so the bottom of the spectrum, which means E, the energy around which, so I'm sorry, I should have done differently, but so you recenter around some energy E, which may depend on L, and so the regime is defined in terms of E. So here, E is of order log L to the 2/3, as in Makin results. Okay, so at the bottom. Then we have what we call the bulk regime, where E is of order 1. Then a crossover regime, where E diverges but not too fast. The critical one, where E is of order L. And finally, the top of the spectrum, where E is much larger than L. So the first question was, what happens to the eigenvalues? So to the local statistics of the eigenvalues. So again, you zoom around such an energy E in such a way that the typical spacing between eigenvalues is of order 1. And this can be done explicitly using the density of states. Okay, so you rescale properly the point process of eigenvalues. So regarding the eigenvalues, what do we get? Well, up to the crossover, we get a Poisson point process whose intensity depends on the regime. So at the bottom of the spectrum, we get an exponential intensity, and in the bulk and the crossover, we get a constant intensity. And by the way, this is completely consistent with Makin result, because if you look at the law of the first point starting from the left of such a Poisson point process, so the first point to the left, it follows a Gamble law. Okay, so it's consistent. Now, if we look, so I need more space, I think here. If we turn to the other extreme, so the top of the spectrum, then we get what people call the picket fence statistics. So everything becomes deterministic, and everything behaves as if we only had minus Laplacian. So it means at this order, the noise doesn't have any impact anymore. Okay, so you have regular eigenvalues, deterministic ones. And in between, we get the ACH tau point process that was introduced by Klitschewski, Valko, and Virag in 2012, I think. So I think I didn't, I was not wrong on the accent, because yesterday I felt that it was could be a bit dangerous to make mistake on these accents. Okay. Yeah. So, and this point process, according to it's parameterized by this tau. This tau is related to the relative values of E and L. And according to this tau, you can recover either Poisson statistics or picket fence statistics. Okay, so it's an interpolation regime. Fine, so now what about the eigenfunctions? So what do we ask to the eigenfunctions? We look at the eigenfunctions which are normalized in L2. So you can see them as probability measures on minus L over 2 L over 2. And the first question is, where is the mass? Okay, so you have a Brody measure. Is the mass concentrated somewhere on a tiny region of the segment, or is it spread out? So localization. Oh no, okay. Let me state things like this. So actually, up to the crossover, it's the localized regime, and above it's the delocalized regime. And so more precisely, you can ask, what is the localization length? That is the size of the region on the segment minus L over 2 L over 2, on which most of the mass is concentrated. And this size depends on the regime. So in the bottom, this size is of order 1 over square root of the energy. In the bulk, it's of order 1, and in the crossover, it's of order E, the energy. And here you can guess why the critical region is critical, because when E approaches L, the mass starts to spread out over the whole segment. Okay, so it's consistent. And here it's delocalized, so you have mass everywhere. And actually you can say much more. You can describe the behavior of the eigenfunctions near their localization center. Okay, so you can describe the shape of the eigenfunctions.
So this is with Dirichlet boundary conditions?
Yes, but it doesn't make,
It won't be
yes.
any different?
No, it wouldn't be, I mean, Neumann would be the same. Actually, we proved, in the bottom, we proved that this is the same. We even have a coupling.
But it's, I just not appreciate the attitude.
Okay, so what about the shape? So let me describe things in the bottom first. So in the bottom, so you have your segment minus L over 2, L over 2. And say, let's look at the first eigenfunction. So what does the first eigenfunction do? So basically, it chooses some uniform point, U1, which depends on L. So asymptotically, U1L will be uniform. And at this point, the eigenfunction will be maximal, and it will follow such a shape. Okay, so very roughly, the width of this shape is, of course, the localization length, so it's tiny, because E goes to infinity, so this width is tiny, and the height is of order E to the 1/4, I think. Yep. And actually the shape, under the scaling, here what do you see? You see a deterministic function, which is the inverse of a hyperbolic cosine. You see the inverse of a hyperbolic cosine, and you would see the same whatever eigenfunction you look like. So it's true for the first, but it's true also for the kth, whenever k is fixed with respect to L.
But the
Okay.
eigenfunction has k zeros.
Yeah, so, okay, so you're right. So that's for phi 1. And so, okay, let me draw phi 2. So phi 2, I need to change color maybe. So phi 2, it chooses another point, independent and uniform. And okay, so bad choice. Yeah, no, it's fine. So phi 2 would do exactly the same. And then it would have also a tiny hill here. But actually, there is exponential decay of the absolute value. So you lose a lot of, the height here is exponentially small compared to this one. So it also follows a hyperbolic cosine, but tiny compared to the first one. And you can continue playing this little game, and you have a full description of the coupling of these eigenfunctions. Okay, so if I have time, but I see that I'm running out of time, I will make some comment about higher dimension on this question. Fine. So now, if we go further into the spectrum, in the bulk, what do we see? In the bulk, we see something which is also uniformly distributed. So you look at an eigenfunction whose rank is k, and k goes to infinity with L at a certain speed. I don't give it explicitly. And what does it do? Well, it would be of order 1 and oscillate at order 1. Okay, so you would see something like this. Okay, so it's not a very good picture. Okay, so here everything is of order 1. Now, if I go further into the spectrum, I see
These let's say, profiles probably exponential, right?
exponential at order 1.
Yes.
I'll make a comment afterwards. I have now 2 comments to make, but okay. And if I go further into the spectrum, it's still a uniform, but now the oscillation become wild. Okay, so the oscillations are extremely wild. The length here is also of order E. The height is therefore square root of E. And the nice thing is that although you have very wild oscillation, actually you can
identify a shape here, which is random, okay? And this shape is the exponential of a two-sided Brownian motion, so let me call this point U. So a two-sided Brownian motion W, centered at U, say, minus the absolute value of a linear function. Okay, so you have an exponential decay due to this term, and oscillation due to the Brownian motion. Yeah, so here I forgot about rescaling, so it's true at scale E. Okay, so you need to rescale things with E. Okay, so if I zoom at scale E here, that's what I see. And actually, this is a shape that arises in a work by Rifkind and Virag in 16, I think, from similar models in random matrices. So, and they conjectured that such a shape should appear in many contexts. Now, what about the critical shape, the critical case? In the critical case, things are delocalized. But the nice point is that, well, you still see these strong oscillations, but the decay is not strong enough to imply localization. Okay, so here you also have a decay exponential, but not strong enough to get localization. But the nice point is that, again, this shape, which is here, is actually the same. It's exactly the same shape. The difference is this, in this case, this shape is restricted to a bounded interval, while here it's on the full line, okay? And that's why you will see localization here and delocalization here. Okay. Fine. And finally, in this case, well, the decay, the exponential decay is tiny at first order, and so you don't see anything. So you just see a very wild oscillation like a sine. Okay, so what? Yeah, I have a first remark to make, which is I started by saying I try to convince you that more things happen in HL than in H. So actually H, the full space operator, is the limit of what happened in the bulk. Okay, so that's typically what you see for the eigenfunctions of the full space operator. But when you take the limit L goes to infinity, you don't see in the limit what happens here on the two extreme sides, okay, negative and positive eigenvalues that diverge. Okay, so it's something that you don't see anymore in the operator H, at least at order 1. And my last, okay, so I'm running out of time. Maybe, if I may, take 2 minutes to say a comment of what happens in higher dimension. So in higher dimension, you can ask, so the operator makes sense. As I say a few words previously about the construction, you need to renormalize the operator in high dimension. But still, you can ask what happens for instance, the first eigenvalue. Is there something analogous to what Mackin showed for the first eigenvalue? So there is a work by Schuck and Van Zejland. 20, and for dimension 2, and with Yusheng Su, which is in the audience, we proved the analogous result in dimension 3. And so what did we prove? We obtained that the first eigenvalue, lambda 1L, it goes to infinity at a deterministic speed, which is something like this. I hope I'm not wrong. Am I correct this time? Okay. Right. Okay.
What did you write?
What did I write?
What is the explanation?
Okay. I'm zooming in here. So it's 1 over 2 minus d over 2. So In particular, in dimension 1, it makes it equals 2/3. So it's consistent. What is CD? CD is related to the optimal constant in the Gagliardo-Nirenberg inequality. Okay, so I'm not stating. So it's not exactly the constant, but it's almost a constant. So it's the optimal constant for this inequality. It's a gradient f L2 to some power times f L2 to some power. Okay. I will make a mistake on the power. But you have an optimal constant here, which depends on dimension, and CD is related to kappa. And then with Yusheng, we have a conjecture about what the eigenfunction do. We have a conjecture about what phi1 lambda, what phi1L should do. So the conjecture is about if we believe that phi1 lambda is, phi1L is localized, and if we zoom in around the localization center as we did with law, we conjecture that the shape that we would see is the shape would be the unique positive and radial solution to this equation. So this nonlinear PD, this type of PD were studied in the 80s. Actually, this Q is up to translation, dilatation, and stuff, the unique optimizer of this inequality. It's not explicit in dimension 2 and 3, but in dimension 1 it's explicit, and you recover the inverse of a parabolic cosine. Okay, so it gives some idea of why the inverse of parabolic cosine arises. So, thank you very much.
Thank you.
Questions, comments?
Sorry? Ah, it's a minus. Thanks.
Just minus the limits multiplied minus everything.
Yeah.
So when you go in the book and you get the eigenvectors, so you go in the infinite point, look at the eigenvectors and you vary the lambda, and you go towards these other things that are next to the bulk, whereas it's not true. Like when the lambda is very small or very large.
Yeah. Right, so actually, yes, so you mean...
You have an infinite volume that changes
Yeah.
lambda, the eigenvalue.
Yeah, sure. So if you are in infinite volume, you can look at what happens near some energy that goes to plus infinity, for instance, and yeah, you would recover this type of behavior. Yeah, and also you can ask things about at the operator level. So Laure, this afternoon, I think we'll talk about the operator level here. And at the moment, we are also working at some operator that should arise in this region. So yeah, but definitely you can take limits at high energies. More questions?
I guess you can't reach the top, right?
No.
It's only the
No, true. So actually, you would get you would reach this crossover regime somehow.
Yeah.
Not more.
How about the cosh? You get that somehow for go the other way?
Yeah. So so if you look at definitely. So if you look at small enough energies, you would also see this this inverse of a parabolic cosine. So actually, I didn't say that there is. We didn't cover some regime in between. But this regime in between is essentially the same as the bottom somehow. Okay, so the paper that we wrote on this bottom case can be pushed a little bit further to cover a little bit more of energies, but not the whole regime for technical reason, probably. But in terms of behavior, everything is the same, except that the intensity will become d lambda as well if you are in the region here in between the bottom and the bulk. And this kind of behavior, you can get them from the infinite volume operator at negative energy, I mean, at diverging negative energies, I think.
The higher dimension case, when you are interested only in the Anderson localization, then we really have to go through this renormalization story, because why can't one do it in such a way that you put a regularization on the noise, try to compute the localization length by more traditional method, and then prove that this is uniform in the regularization. Because some of what you are saying, the renormalization requires to subtract an infinite constant, but on the other hand, the eigenfunction should not depend on that.
That's true, it's only a shift in the spectrum. So in terms of eigenfunction, it doesn't make any difference.
So usually what the physicists would do in that way, they put a regularization there, they don't care so much about how to remove it, but mathematicians could try to say that it's uniform in the regularization, and then
Yeah, right. Yeah.
higher square.
True, but the thing, okay, but in the end, it's not so much of. For instance, proving, okay, it's work in progress, but the renormalization is not so much problematic for dealing with the operator. So I don't try to do as you propose. That probably it would be a good option, but in practice, dealing with the operator, even if it's renormalized, is not so much a big deal. Yeah.
Because you spend some time on defining the domain precisely, and then that it's not the main part of your job.
No, so okay, construction of the operator is done somehow. Not exactly in the full space, there are still some things to do. But when it's constructed, you don't have to bother too much with renormalization, I would say.
So you said the localization was work in progress using
In 2D,
which technique?
multiscale.
Multiscale.
Multiscale. But it's hard to, I mean, for experts probably it's.
Did you try Eisenman Molchanov?
I should, so I had discussion with Frederic Klopp on that. Okay, the thing is, all this is hard to me, so it takes me time to learn that stuff. But probably for experts it would be doable.
More questions? Well, if not, let's thank Cyril again.